Hello, my name is Tyler Stupp, and we are with To the Point of Science. My guest here today is John Ragusse. Is that how you say your last name?
Yep, you got it.
And
I work in the physics building and in the Engineering Resource Center, the ERC.
he works on improving the efficiency of solar panels.
Yep.
And John, before we really get into the meat and potatoes of your research, how about you give us just a little bit of background on yourself?
All right. Well, I am a grad student at CSU. I did my undergrad at Michigan State University, and I am in my fourth year, and I'm starting to write my thesis, and hopefully I should be done with my PhD in the spring.
And where'd you do your undergrad?
Michigan State University, East Lansing, Michigan. Go Spartans.
All right, go Spartans indeed. Tell us about the first part of your thesis using the photographs.
Okay, yeah, so I developed this tool that measures this signal. Basically, I take pictures of solar panels, and what happens is, so solar panels, so the idea is you put light into them and you get power out. Well, you can put power into them and it gives off light. It works identical to LED, so a light-emitting diode, which we have everywhere. And so as one process is more efficient, so the process of converting light into electrical power, if that's more efficient, then the inverse process, the opposite process of converting electrical power into light is also more efficient. So part of my thesis works on taking these images of the light that the solar panels give off, and we can tell how efficient they are. And more so, it's used as a quality technique in industry. And so as you make a solar panel that you would put on your roof or for utility grid, the big, maybe 3-foot by 2-foot solar panels, at the end of the manufacturing line, you can put power into them, have them give off light, and take an image of this light, and based on that image, you can very quickly look at the defects that exist within those solar panels. And so by knowing what defects exist, you can then go back in your manufacturing process and solve those issues, thus increasing the efficiency of the module.
And exactly, in a solar panel, what causes a defect?
So what causes a defect? So we work on a type of technology called thin films. And so the reason why it's called a thin film is because it's 5 microns thick. And so to give you a reference, your hair on your head is about 50 microns in diameter. So the whole thickness of the solar panel is 1/10 of the width of the hair on your head. So it uses very, very little material. Well, one of the layers is only 100 nanometers thick, and it's very, very difficult to deposit 100 nanometers uniformly over this 3-foot by 2-foot piece of glass, or 4-foot by 2 feet, or 5 feet by 2 feet. Depending on the manufacturer, they have different sizes. And so that's one cause of the defects, is the uniformity in the thickness. And another problem, a common problem that we find, is when you make a solar panel, you want to cut the solar panel so that it goes from one big cell to a bunch of small cells, and they're all in series, so the current goes through each cell. And as you cut these they're called line scribes, and as you cut them, if you miss a spot, so if you don't cut the whole line uniformly, if you miss a small spot, you'll get a short in the solar panel. And that short, that's a problem. That's one of the cells in that solar panel will now be consuming power, and all the other ones will be generating power. So you've now lost some amount of power output.
And that's because you have a smaller cell making a smaller circuit inside of the big circuit?
Yeah, so that's because the current completely bypasses one of these cells. And so what you want to do is these line scribes are really, really small, because if you have a certain area that you deposit the solar panel on, the smaller the line scribes, the width of the line scribe, the more material you have to generate power. So you want to make these line scribes as small as possible. But in doing so, it adds this problem of, well, you may not cut them very well. And there's actually 3 lines per scribe. So in order, you have to make these cells, because if you didn't, these solar panels would be operating at something like 100 amps at 0.7 volts DC, and that it makes it very difficult to match it with the grid. So you want something that's more like 60 volts. So you cut these cells really small so that you end up with a large current or a large voltage and a smaller current.
Okay, and so you can find such imperfections in a solar panel using the light that it gives off.
Yeah.
And you photograph that. Now, talk about how that kind of relates to the phrase that making a better solar panel is really making a better light bulb.
Okay, yeah. So it goes back to this idea that these processes are inverted. That is, putting light in, you get electrical power out, and putting electrical power in, you get light out. So instead of, for example, if you wanted to engineer a better solar panel, because this is true, because, a better light bulb, as a solar panel acts like a better light bulb, it acts like a better solar panel, you can completely forget about the engineering behind the actual solar panel and say, well, let's just make it a better light bulb. And in doing so, by making it a better light bulb, it will also become a more efficient solar cell or solar panel. And so there have been companies in the past which have gone with this approach. And so there's this one company where they put a mirror on the back of a solar panel. And by putting the mirror on the back of it, it reflected the light forward, so it gave off more light. And they were able to break the record. Again, they broke the record before that. And then once they put it on a mirror, they broke the record again. And actually, interesting enough, my advisor gave a talk at a university about a year ago, and he showed this plot that I made of, on the y-axis it was light intensity, and on the x-axis it was basically efficiency. And you could see this line where the solar panels that were more efficient gave off more light. And when he did that, this was this formal talk at Purdue, one of the gentlemen who worked for this company, where the company who recently broke the record by putting the mirror on the back, they jumped up in the middle of the crowd, interrupted the talk, and yelled, "I told you so!" And which is not very common for professors, especially people that are distinguished and break these world records. So it's kind of a new thing, and a lot of companies are very much so interested in it. And the project started out from a local solar panel company who gave us funding, and they said, okay, we want you guys to develop this so we can put this on our manufacturing line. And we did that. And so they were really pleased with it, and oftentimes we have companies send us their solar panels and ask us, they're like, hey, when we make a really, really small solar panel, so something like maybe the size of a quarter, they're maybe 15% or 17% efficient. But when we try to make these huge modules, these things that you would put out in the field around your house, they're only, let's say, 10% efficient. And I said, we don't understand this loss. Where is this loss? Why is it that we can make these really efficient small ones, but as we get bigger, we lose this efficiency? And so they'll send us modules, and we can characterize them for them.
The second half of your thesis is coming up with a way to minimize this loss, correct?
Yeah, so the second part of my thesis is making the next generation solar cell. So there's a group of us that are trying to, we received some funding to further develop technology. So the technology that we spend most of our time in is known as CAD-TEL, or cadmium telluride solar panels. And so the material which absorbs the light and converts it into electrical power, if you will, is the cadmium telluride layer. And so we want to put another layer on the back of that, and we're hoping to, by doing that we will increase the efficiency, and industry will most likely adopt it once we've developed it.
All right. Now, I know this isn't the question you want to be asked because it involves quantum mechanics. Everybody, this is going to be a doozy of an answer. But explain to us exactly how does a solar panel work, and what are you doing with that to make the next generation of solar panels.
Okay. Okay, I'm going to use the parking lot analogy. All right, so imagine you have a parking lot, a 2-level parking lot. So you have this ground floor and you have this second floor.
And the different levels of the parking garage actually represent different levels in the energy band.
And imagine you have all these cars on the bottom level of the parking garage.
And in this analogy, the cars represent valence electrons.
And so one of the cars will go from the bottom level to the top level. And so imagine the second floor of our parking garage, imagine it's slanted, if you will. There's a slope. So as soon as the car goes up there, it sort of rolls down the hill. And once it leaves the front, then it completes the circuit. So it goes through your computer monitor or your fridge, and it powers whatever load you have hooked up to the solar panel. And this is ideally what happens. So this car goes from the bottom to the top, and it rolls down the front. But sometimes what happens is, imagine there's also a back entrance to the parking lot, to the second level of the parking lot. And that's also sloped downwards. So the cars that go from the ground to the second floor towards the back of the parking garage, they'll roll down the hill, but they'll roll, and as they do that, that is power loss. So that won't go into powering your fridge or powering your whatever you have hooked up to it. It will heat up the cell, so it's power loss. So what we're doing is we're trying to put this layer on the back. So that would be for the cadmium telluride layer. That's the analogy I just gave. So now we're putting cadmium magnesium telluride on it, so we're alloying it with magnesium. And what that does is, imagine now we have a second parking garage that's hooked up to the first, and again there's 2 floors. But now the second floor is higher than the second floor of this second parking garage is further higher up than the second floor of the first parking garage. So cars that would go into the first floor, they wouldn't roll back. So that slope is no longer there. It's sloped up, and the car is not going to roll uphill. It's not going to roll up into that second parking garage that we just put on the back. And so, yeah, right. So we're trying to minimize, it's known as recombination. So the electron will recombine in the back, and if we put the slope there, it won't recombine, hopefully.
Okay, so essentially, your valence electrons are going from the valence first floor of the parking garage and are being swept into the second floor of the valence electron parking garage to complete the circuit and kind of generate energy.
So anytime you have a current flow, that's a movement of electrons, and those electrons have to move within the conduction band. So the second floor is the conduction band, and the first floor is the valence band. Yeah, so you need a particle of light where the energy of that particle is at least that difference in energy between the first floor and the second floor. And if an atom sees that, then it will excite the electron into the conduction band. And it's still bound to the actual material. It's still a part of the material, but now it's no longer bound to a specific atom. Now it's bound to the whole lattice. It can move freely, but it can't leave. It can't jump out.
So what does this parking lot do in the overall function of your solar cell?
Yeah. So it prevents, in the back of the solar cell, the electrons that go into the conduction band, so the cars that go into the second floor, they will leave through the back of the solar panel, not through the front. And when they leave through the back of the solar panel, they recombine. And so really what happens is, as this electron goes into the conduction band, it leaves behind the absence of electron. So if this atom was once neutral, and now an electron left that atom, it now acts like this absence of an electron in the atom now acts like a positive charge. We call that a hole. And the holes, because they're positively charged, we do treat them like they're particles, but it's not a particle. Those are swept through the back of the solar panel, and you want holes to leave the back, and you want the electrons to leave through the front. They're oppositely charged, and in an electric field, they go in opposite directions. But if an electron wanders into the back of the solar panel, it'll see a hole, it'll recombine with the hole, and it will heat up the solar panel. So the analogy is the cars that go from the first floor to the second floor. If they're towards the back of the parking garage, then they'll roll downhill, and let's say they crash into, something, right? This terrible thing happens. And so you want to minimize that. That's a loss. You want the cars to go out through the front, not through the back. So we put this second parking garage right next to it, again, where the second floor is higher up, so that the second floor of the parking garage towards the back, it's not sloped down, but it's sloped up. So the car is not going to roll up the hill through the back. It will simply leave through the front.
Okay. And why is it important that the cars go to the front of the garage? What does that do?
Well, as they leave the front of the garage, let's say they enter the road and they're moving at some speed. They have energy, and they can give that energy up to powering whatever it is you want them to power.
Okay. So this is really important to contributing to whatever it is that powers. So keeping the cars out of the back of the garage, or conversely, the electrons from crashing into the back, really makes the solar panel more efficient.
You make a solar panel more efficient. You output more energy,
Okay. And so you've got these two layers of these two parking garages are cadmium telluride and magnesium.
And magnesium telluride.
And why use these two different materials?
Okay. So cadmium telluride is a really nice material to work with, in that it's very inexpensive. So when you want to make a solar panel, the technique used to deposit the materials, you can deposit the material very easily. Okay, so that's one. Two, it's known as a direct bandgap absorber, which means that you do not need a lot of material for it to absorb a lot of the light. All the light can be absorbed within 1 to 2 microns. And the material, again, hair on your head is 50 microns. So you don't need a lot of material. Thirdly, the band gap, so this energy difference between the first floor and second floor of the parking garage, as you change those heights, the maximum theoretical efficiency of the solar panel changes. So the height of the second floor relative to the first floor is almost ideal. So the maximum theoretical efficiency of these solar panels is about 30%. Okay, so they're cheap to make. We don't need to start with very high quality materials. And at the end of the day, the cost of the solar panel ends up being roughly the cost of the glass because you use so little material. So then now on to your next question. Why use cadmium magnesium telluride, or we can abbreviate that as CMT? So we add small amounts of magnesium to it. We're alloying cadmium telluride with magnesium. And so CMT grows really well on cadmium telluride. If you want to grow one material onto another, there exist certain properties which need to match in order to grow those materials on top of each other. So, for example, the distance between the atoms, those need to be the same. You can imagine if we have a room and you fill up the room with a bunch of golf balls and the whole floor is just covered with golf balls, and let's say that's one material, and the distance between those balls, that is known as the lattice constant. These are the distance between the atoms. Now, if you wanted to put another material on that, the spacing between those atoms need to be the same. So you couldn't take, let's say, a beach ball and grow and put beach balls on top of all of those little golf balls because they're not going to sit well on top of the golf balls very well. It's not. And then so if you tried to do that, then this second layer, which is represented by the beach balls, that would just delaminate. It would peel off. It wouldn't adhere. And the third thing is that it would appear to be fairly straightforward to, if you're depositing CAD tile, And if you want to then deposit this following material of CMT, you could just add a little bit of magnesium to it. So it's a small difference in the manufacturing process. You're not really adding a whole lot, but you're gaining a lot of you're gaining efficiency by doing that.
And how are the solar panels that are coming with your new generation? What tweaks do they have that the old generation didn't have?
So they have this second parking garage. They have this CMT layer on it. So solar panels today, the cadmium telluride solar panels which exist, are simply that. It's just cadmium telluride. So they just have the one parking garage. So you have this recombination in the back. You have these cars, on the second level, and, it's sloped down, and let's say the cars are crashing as they're leaving. So the next generation hopefully will have this second parking garage on it.
Okay, and that will eliminate recombination, which is efficiency lost in solar panels.
Yeah.
Because those valence electrons or the photons?
So the electrons in the conduction band recombined with the holes in the valence band, and basically what ends up happening is the cell heats up. So energy is conserved. The car,
Right.
Instead of rolling down, it literally, let's say, just crashes down.
Right. So right now there's a lot of opportunity for for the electrons to plug those holes in the valence band, which heats up, and your second parking garage or this new layer stops that by creating the upward sloping so it can't crash through the back.
Right. Yeah, so the cars can only leave out the front and they cannot come out of the back.
Right, which equates to less efficiency lost.
Yeah, it's a loss mechanism. The solar panel heats up, so the energy goes into heating up the solar panel instead of powering something else. And we don't want that.
What are some of the challenges that you face researching making a solar panel more efficient? Because theory only takes you so far.
Yeah, it does. I read this saying once, and I think it's true, and I really like it. If we knew what we were doing, we wouldn't call it research, right? So you do a bunch of modeling. You say, hey, look, if you add this other layer, you should see this, that, and the other thing, and at the end of the day, it should be more efficient. Okay, great. So you put that other layer on, but you don't know what temperature to deposit at. You don't know what pressure to use. You don't know. There's so many things that go into it. You don't even know what the ideal height of that second parking garage should be. Because there are things which exist in real life where models don't necessarily take into account. All models are wrong. Some are useful. Okay. And you just hope that the models which the previous graduate students have written, you hope those are useful. You hope they're sufficiently accurate so that they guide you in the right direction, but you don't know. If it was easy, it would have been done by now.
When you say that you hope that their models are right, does that mean you basically redo their experiment to some extent, or do you just literally start from scratch, use that as a reference kind of, but don't take it for granted?
Yeah, you use it as a reference. You say, okay, so this person did some modeling, and they said that you should, and the models say that, hey, if you deposit this second material, then these are the different parameters you should see when you measure the solar panels. Or when you measure the solar panels, this is what these different curves should look like. And there are a lot of things that, if you actually then put that second layer on and you make the measurement, and if it doesn't agree with what the model says, then where are you? Do you say, well, are they right? And there exist other defects, other problems, which we are not taking into account? Or is it something more severe? And there exist many parameters that are very hard to encompass in a model. And so you do the best you can with modeling. And, you come up with these results, and then you just have to try to make it. And you just have to try to build it, and you just have to go for it.
So personally, in your project, your thesis, what have you kind of found that you really didn't expect? What did you find which kind of went against what you thought should be common sense, or what should be law, what should be theory? Did you have any of those moments?
What ends up happening is you realize how many knobs there are to turn. And we could make something like 8 solar panels in a week. And so if you make 8 solar panels in a week, and let's say there's 10 different knobs, well, that's a lot of solar panels you have to make to span that whole space, because each of those knobs you hope are independent. So it's the realization that you have to sit down and pick your battles, and you have to sit down and say, okay, guys, which knobs are most important? And let's try to turn those knobs this week, and then let's measure those solar panels, see what we get from turning those knobs. And then hopefully that provides us with some insight, and then the following week we change different knobs. And you really try to get a feel for what's going on. Because you take a stab at it, and you don't know. Maybe with CMT you need higher material quality than what we've been accustomed to. Maybe it's possible that the first floor of the parking garage, of those 2 different parking garages, maybe the first floor are not at the same level. Maybe one's offset from the other. And that creates problems. And then how do you fix that? Okay. And then you come up with ideas how to fix that. Or the sheer fact of attempting to measure that is incredibly difficult. And realizing that, you could give someone $50,000 and they still can't tell you how much that offset is. There are a lot of things that are very, very difficult to measure. And much of that is because you want to measure what's going on the inside of the solar panel, not on the surface. And oftentimes when measurements are done, you can only measure the surface of the material. And then you say, okay, well, let's dig in further, and then, let's go to where these 2 parking garages are together. Okay, so you dig in further, and you see this material, but because it's being exposed, inherently, you're not going to measure what you think you're measuring. So it's very difficult to measure the inside of the solar panel. So there exist these types of challenges where you try to figure things out, and you try to figure out what's going on the inside. And every experiment you do, and every measurement you do, it's telling you something. It's right. You did the measurement. The measurement's right. The data's right. How does that agree with simulation? What is that telling you? And that's a really hard thing to do.
But it's satisfying.
Oh, yeah. I get to wake up every day thinking I'm solving the world energy problem. I mean, that's incredibly satisfying. And all of us who work in the labs, we all feel the same way. And it's a really great feeling to have. And, we feel like we're doing something that's a really noble cause, and we're doing something which we feel is very important. And oftentimes, many graduate students work a lot of hours, but it's nice when you're working on a project that you feel like you have an impact on things. You really feel like the results of your work are incredibly important and can change the world. That's a really good feeling to have, and that's a really nice place to be.
So, now, looking into the future, because I imagine solar panels is a somewhat competitive field, if there are things like records for efficiency and whatnot, right? So, how fast does solar panels, like, as a commodity, how fast does that innovation happen, would you say?
Oh my God. Right now, the growth is unbelievable. So the overall installed solar panels worldwide has grown 40% a year. So there's a company which last year they made more solar panels. So it's exponential growth. So last year they made more solar panels than all the solar panels that they've made total. I mean, the growth is unbelievable. And there exists much competition between different companies. and there exists a lot of competition internationally. So cadmium in of itself is toxic, but it's bonded with tellurium, and so it's stable. Cadmium telluride is stable in the same way that, when you eat table salt, which is sodium chloride, sodium in of itself, if you had a chunk of sodium and if you threw it in water, it would light on fire. And chlorine in of itself, chlorine gas, will kill you. But we eat table salt on a daily basis because when those two atoms bond, the properties of that new molecule is no longer the properties of the individual atoms. So anyway, so there's some countries who would prefer not to do work or prefer not to have cadmium telluride-based solar panels in their country. But then there exist other countries who are a member of the World Trade Organization, and they are not following the rules of the World Trade Organization. And as a result of that, companies in the U.S. have gone out of business, which is unfortunate because there was quite a bit of lag between the government recognizing this. It took quite some time before the U.S. government put tariffs on these imported solar panels, and they were allowed to put tariffs because those countries were violating the World Trade Organization. And it's incredibly competitive between different companies. Yeah, absolutely. The energy industry is projected to be the world's first trillion-dollar industry. And if you think about it, just the amount of people in India and China who are entering the middle class, they want fridges. They want to consume more power. That's effectively what happens as a country becomes more developed. You have less expensive electricity and you need more of it. So not only do you have exponential population growth, so you need more and more power to provide for those people, but you have more and more people entering the middle class, which is putting a higher demand on the electricity grid, just demanding more power. And solar is a really nice way to do that. It's a really convenient way to produce that power. So the growth is astronomical, yeah.
And so, with such competition, the rate of innovation must be, somewhat parallel to that, right?
Yeah, absolutely. That's the name of the game. So, at the end of the day, what matters is the cost per watt. So how much does it cost you to make that solar panel divided by the electricity output of that solar panel, right? So in other words, I can sell you a solar panel that's 50% efficient, but it costs 10,000 times more than a solar panel that's, let's say, 10% efficient. That 50% solar panel is not cost effective. So that's why we work on cadmium telluride, because it's very inexpensive. The majority of the cost is the cost of the glass. And solar panels are a commodity, so they're all sold at the same price. So the profit margins is just the difference between what you're selling it and what it costs to make it. So one of the larger companies, First Solar, they're investing something like $120 million a year in their R&D. And the more efficient they can make their solar panels, the more competitive they are. And there's something like maybe quite a bit of the companies. There exists a lot of solar panel companies now, and 5 years from now, not all of those will probably be around because their ideas may not pan out as well as some of the other companies.
Right, which is just what you get when you have an open market system for good.
Yeah. Yeah, so our lab gets much funding from industry because we're grad students and we're cheap labor, and we can afford to spend 3 years studying one type of material where that's not as easy in industry, and we can do sort of the very preliminary research, and then they can take it and optimize it.
So, and because innovation's going so fast, this might be hard to answer even, but say in 10 years, where might solar panels be at?
Yeah. So,
like, just what's next for solar panels?
What's next? Yeah, so, well, let me tell you where they are right now, and then we'll talk about 10 years from now. So again, this company, First Solar, they just sold a power plant to a utility company out in Arizona. Well, it was First Solar and General Electric. They sold it to this utility grid. And they sold this whole system. This includes the cost of borrowing the money for less than 6 cents a kilowatt hour. My electricity bill here in Fort Collins is something like between 8 and 9 cents a kilowatt hour. So right now obviously they sell that to the utility company, and then the utility company marks it up and they sell it to you. They have to recoup their costs. They have to pay back these loans, etc. So right now, and the land in Arizona is relatively cheap and it's very sunny. So in the status quo, there exist places in the United States where it's cheaper to get your electricity from solar panels than it is from conventional sources. And actually, New Jersey is one of the larger. California is the largest installer of solar panels, or most of the solar panels are in California, but New Jersey is one of the top 3 states to have solar panels. So that's where we are right now. So things are looking really well right now. And the name of the game, so there's 2 different games that they're playing. There's one game where we say, okay, let's make them more efficient because we use so little material. The CMT layer that we put on, it costs nothing per solar panel. But if you can get another 1% increase in absolute efficiency, so let's say you're going from 17% efficient to 18% efficient, over the life of the module, so over 25 years, that extrapolates to huge amounts of power gained. So that's one name. Let's make them more efficient. The other name of the game is economies of scale. So as the industry grows, you make your plants bigger, you make more solar panels, they cost cheaper per unit. So 10 years from now, they're going to be a lot less expensive and they're going to be a lot more efficient. There exists a well-defined learning curve for the industry, and the companies have met it. Similar to sort of Moore's law, with processors. The companies have sort of been following something similar, that the cost per watt has been going down as time goes on. So 10 years from now, I don't know where they'll be, but hopefully it's going to be a major source of world electricity. And it's just grown astronomically, and it's just going to continue to grow. There's really no limit on the growth. Right now it's less than 2% of the market in the U.S. is solar panel, and so there's a lot of penetration in the U.S. market and the world market. And we expect to see solar panels all over the place. We hope to see them all over the place.
All right. We're just at about 42 minutes, so this will be our last question. That's what's next for solar panels. What's next for John Ragusse? After your thesis, what's the next thing you want to study? What are your plans after this solar panel project?
I haven't figured that one out yet. I don't know. Solving the next interesting problem.
All right. Well, there you have it. Everybody, you're listening to 90.5 FM KCSU, Fort Collins. Today we have had John Ragusse on. He works in not the engines lab, the physics lab, creating the next generation of solar panel. John, thank you so much for being on with us today.
Thank you for having me.
You were a pure pleasure, and we will be back next week with